Problem 6.2-1. Determine the bending stress at points A, B, C, and D. Theta is equal to 20 degrees. Here is a C channel, and points A, B, C, and D are the corners. And there is an unsymmetric bending moment being applied, and here is the angle theta. It's 20 degrees. The first thing I'm going to do is find the vertical distance to the centroid of the cross-section. This will tell me where the neutral axis is for bending about the z-axis. I'm going to make a table of values so that I can calculate the centroid location. First thing I'm going to find is the distance from the datum point, which I've chosen to be the top of the cross-section. The distance down to the centroid of each piece 1, 2, and 3. So for piece 1, which has a height of ½ inch, the distance to the centroid, or this y tilde value, is 0.25 inches. Piece 2 is 2½ inches tall. Half of that is going to be 1.25 inches, and plus the thickness of piece 1 up to the top, another ½ inches gives 1.75 inches. Okay, I found the area for pieces 1, 2, and 3, and then I multiply y tilde times the area to get this value here, and I can calculate the vertical distance to my centroid, y bar. That's equal to the sum of the y tilde times a divided by the sum of all the areas, and I get 5/5, or 1 inch. So our neutral axis is 1 inch down from the top of the member. Now to find the location of the neutral axis for bending about the y-axis, we're going to want to find the location of the centroid in the horizontal direction. And because this cross-section is symmetric about the y-axis, that means the neutral axis is on the y-axis. Okay, the next step is to find the moment of inertia about the z-axis. And I'm going to use the parallel axis theorem to do that. It's shown right here, and I've just made a table again like I did above, where each piece is the same as it was above, and for each piece it's a rectangle, so I use the moment of inertia equation for a rectangle, bh³/12. Then I just get the area that I've already found that in the table above. I just pulled that down. Then the d value is the distance from the centroid of each of the pieces to the neutral axis, and it happens to be 0.75 for every piece. And then I multiply a times d squared to get this value. I sum up my individual moment of inertia values, I sum up my ad squared values, add them together, and I get my total moment of inertia is 4.167 inches to the fourth. Okay, to find the moment of inertia about the y-axis, we can essentially take our cross-section and flip it. So now that the y-axis is showing as horizontal, and piece 1 is still the same piece, but the values for B and H are changing relative to the moment of inertia values for moment of inertia of that piece about the z-axis. And the areas for pieces 1, 2, and 3 stay the same. D values, notice that the D value is 0 for piece 1. That's because its centroid falls right on the neutral axis, so that's D is 0. For pieces 2 and 3, it's 2¼ inches away from the neutral axis for our D values. So get our AD squared, sum up our moment of inertia values and AD squared values, and altogether we get 17.917 inches to the fourth. That's our moment of inertia about the y-axis. The next step is to find the components of our unsymmetric moment about the z and y axes. Now we're going to use this angle here, theta, and because theta is going counterclockwise from the positive z-axis, then that's going to put a negative sign on our theta. That means when we find our z component, we'll take 4 foot kips, and we'll multiply that by the cosine of -20. That's going to give us a positive value. The moment about the z-axis will be positive. When we take 4 foot kips, multiply it by the sine of -20 degrees, that's going to give us a negative component for the y about the y-axis, which makes sense for the quadrant we're in. So let's go ahead and do that. Okay, we found the components of our moments about the z and y axis. Notice that I took 4 foot kips and I multiplied it by 12 inches per foot to convert the units into inch kips. This will be useful because I want my stress to work out in units of KSI. So I need to get rid of the feet here. And for the z component of the moment, we multiplied by the cosine of negative 20 degrees, and for the y component, sine of negative 20. The negative is there because theta is going in the counterclockwise direction from the positive z-axis. If it's counterclockwise, then we'll give it a negative sign. Okay, the very last step is to find the stress at the 4 corners A, B, C, and D of the cross-section. In the final step, we will use the equation for calculating normal stress under unsymmetric bending, and I've filled in the values for mz, my, iz, and iy. And what remains are the values for y and z, which are dimensions of the point coordinate, and those are going to be in units of inches. Okay, let's first look at the y values for points A, B, C, and D. For A and D, they're negative 2. For B and C, they're positive 1. If we look at the cross-section, we see A and D are 2 inches down from the z-axis in the negative y direction, so they'll have values of negative 2 for y, and B and C are above the neutral axis, the z-axis, so they will have values of positive 1 for y. Now let's look at the z values for the 4 points. For A and B, they will have a positive z value, half of 5 inches. That'll be 2.5 inches. Points C and D are on the negative side of the y-axis, negative z direction. They'll have values of negative 2.5 inches. Okay, plugging in values for y and z into our equation, we can calculate the stress at the 4 points. We see that corner D has the highest tension stress and corner B has the largest compression stress. And here's D that has the highest tension stress. We could use the right-hand rule to verify that D does in fact have the highest tension stress, while B will have the highest compression stress. Notice, because this section is not symmetrical about the z-axis, that the maximum values for tension and compression stress are different. And we're done.